In this video, we're going to discuss all the same things regarding hypothesis testing and confidence intervals that we've discussed previously regarding two populations comparing their mean with the population standard deviations known, comparing their mean with the standard deviations unknown, and comparing matched samples. But now we're going to discuss how we look at proportions. So here, I'm going to be comparing proportion 1 and proportion 2. And again, remember your textbook's notation here, and I kind of disagree with this notation, but we should be aware of it. I prefer to use a little hat in place of the little bar. Little bar typically means average, little hat typically means estimate. So I like the hat saying the estimate of the population proportion for group 1, and then the hat meaning the estimate of the population proportion for group 2. So when we're looking at this, just like before, we're using this difference of the two values. To distinguish between what we just talked about with matched samples, we're going to assume we have a whole bunch of different proportions from the first population, a whole bunch of different proportions from the second population, a whole bunch of different data from the first population, with which we can calculate a single proportion, and same for the second population. But we're going to assume that each of these observations of these groups are independent from one another. That is, there's no way to connect the groups. And that's what we did before when we looked at the means for the z-test and the t-test. That's different than what we did with the matched samples. And again, if I don't tell you that you can connect, or if you don't have a really good reason, it needs to be a really good reason to connect them, then you don't. And it's a thing where you don't connect them unless there's a good reason to, and then you do. So in this case, I need my point estimate. So that's what I have here. We can look at the average value of the point estimate. So if I did this over and over again, on average, what would I get? And I get out the population value on average. So that's good. In fact, this is what we call the definition of a lack of statistical bias, or unbiased statistically. This is good. The standard deviation of this value, which is also called the standard error, is the square root, and you'll see that this looks very similar to how we had the standard error for both the z and the t-test, where we have the population 1 stuff, the population 2 stuff, and all the stuff under the square root looks pretty similar to what we had in the individual single population proportion standard error, but we have the single population standard error under the square root stuff plus, from the first population plus the single population standard error stuff under the square root for the second population. So that sounded way more complicated than it actually is. All I'm trying to say is if you pull up your notes and you go look at what this standard error looked like for a single population, we did proportion testing for a single population, or confidence interval for a single population with the proportion, this is going to look very, very similar. And that's good. That's good. You like it looking similar. It's not just adding the two together for the populations, but it is adding them together underneath the square root. All right, so in this case, just like before, we have the notation sub 1 and sub 2 for the different populations, and there are sample sizes for each of the groups. Now, one thing that's slightly different, and these rules are all the same, the slight difference is that these rules have to be obeyed for both of the populations. So we need reasonable sample size for the first population and a reasonable sample size for the second population. So we're looking at both of these together. So this is a picture of our sampling distribution of this estimate. So this is our best guess as to what the population value is. So these ones with the little lines on top, or again, if it's me, I'd have little hats on top, is our guess at what this single value for the population is. So this is analogous to being mu, and this is analogous to being x bar if we were looking at means, but now we're looking at proportions. So here we've got our standard error, so we can go out, a couple standard deviations in either direction. Again, standard error is just the standard deviation of a particular statistic. Putting this all together, we have our point estimate plus or minus our critical value. This is the same as we had in the single population case times the standard error that we wrote out on the previous slide, and that's not too bad. So putting all this together, we have research that we're looking at assessing the effectiveness of an advertising campaign. So before we do this campaign, we're seeing how many people know about our product. So we've got 60 households out of 150 that we looked at are aware of the product. So then we run the campaign, and we see that 120 out of 250 are aware of the product. And we're seeing, are these two proportions different than one another? Are these two proportions different than one another? So in this top one, if I calculate out 60 over 150, I think I get something like 40%. This bottom one, 120 over 250, I get like 48%. Or 0.4 and 0.48. So we're asking, again, are these different than one another? What I need to do, though, is pick the order that I want to do. So I'm assuming, and you can do it in either order, but remember the order changes the meaning. So you could do it in first minus second in the way in which it's presented in the problem. And this would say, okay, the first minus second. So the beginning before the campaign minus after the campaign. So I'm hoping it probably goes up. I'm assuming, yeah, increased awareness, right? We don't want after doing a TV and newspaper advertisements, we don't want less awareness. We want more awareness. So if I want more awareness, that is, I want this second number to be bigger. First minus second is a negative number, right? Smaller minus bigger is negative. In which case, a good thing to happen would be negative numbers, and I'd like negative numbers to come out of that. So if I put the first one as P1 and the second one as P2, then I'd be looking for negative numbers. Typically, I prefer positive numbers to indicate the direction I'm interested in. But you really can do it either way. Just track what order you're doing it in and what that means. So because I want increased awareness, I want the afterwards number to be bigger than the before number. And if I want that to be positive, the after number would have to subtract the before number. Remember, after bigger, hopefully, before smaller, hopefully. So I'm going to put the second values, the afterwards numbers as P1 and the beforewards numbers as P2, so that I can keep these in the direction that I like and make this interval positive. Again, it really doesn't matter what order you do it in. What matters is, can you interpret the outcome given the order that you've done it in? So can you make an interpretation as to what positive and negative means? And if you can, then that's fine. And if you can't, then that's a problem. So I really want to make sure that you're following along with what that means, as opposed to, well, every time the first number goes first. So in this case, again, I'm going to put the afterwards, the second number first, and the before, or the first number second. All right, so plugging these values in, I literally just type it in. The trick is getting z from the table. Remember, alpha over 2 always when we're doing a confidence interval, because we have two sides, the plus and the minus side. So we've got our curve, we've got our cutoffs on two sides. And then I just plug in these numbers. I plug in the values for P1 and P2, my estimates for those. And plugging in those numbers, I get 0.08 plus or minus 0.10. So there was my best guess at a single value is there was an 8% growth from pre to post. That is, the post is 48%, the pre is 40%. So I went up. Or before the campaign, 40% awareness. After the campaign, 48% awareness. But my margin of error, my reasonable range is 0.10 on either side of 0.08. So here, my reasonable range goes from, we could have dropped 2% awareness, or we could have gained up to 18% awareness. So this is my reasonable range of values. First of all, I want to notice here that if somebody says your campaign did absolutely nothing based on this interval, well, a zero change, a change of 0, is somewhere in this interval. It's somewhere between negative 0.02 and positive 0.18. So if somebody said 0 is a reasonable value or no change is a reasonable value, yeah, based on this 95% confidence interval, no change is a reasonable value that could have happened as a result of this campaign. And if I wanted to be more specific, if I wanted to come up with a closer interval, I'd need to go collect a higher sample size, more data, to be able to narrow this down some. Typically, as a rule, if I have a negative number on the bottom of my interval, and we always go lowest to highest. So if it's negative on the bottom and positive on the top, then we know that 0 is in between a negative and a positive number. So if it's negative on the bottom and positive on the top, we know that no difference or no change is a reasonable value. Or said another way, claims that there was a change, well, that may or may not be true, because no change is reasonable to believe based on this data. All right, jumping into our hypothesis test, the constructions are the same as we have had before. We're just looking at the population proportions now. And here you can see that instead of constructing this as greater than, less than, and not equal to D, as we've had before, they just focus on 0 difference, which is pretty common. In fact, this is pretty common even in the comparisons of means. I talked in that video about how I do like the ability to have a difference that's different than 0, but it is worth mentioning that 0 is far and away the most common value. All right, so for a standard error, we have the standard error. Now, what's interesting here is that when we're looking at these two values as being, and I'm going to use this two-tailed one, but our null hypothesis is that P1 minus P2 is equal to 0. Remember from before that this is exactly the same as saying P1 equals P2. So there's a reason that we like this top one. It's because we have kind of a single number here. This difference is a single value. But this is mathematically the same statement. These two are the same. And I should mention, again, I really don't like how the textbook does these. Traditionally, we would write all of these null hypotheses as equal. The textbook does have an equal sign as part of the inequality, but typically I prefer, or I would say traditionally these are written as equal. So here, when we have this difference, looking at 0, what we're really saying is that these two values are the same. Now, why is that important when we talk about the standard error? Well, if these two values are the same, we can just call them the same number. So under the null hypothesis, that is, by our default belief, thinking back to the court case, innocent until proven guilty. So under the assumption of innocence, which we are required to function under until we're proven guilty. So under the assumption of innocence, under the null hypothesis, these two things are the same. And if they're the same, I don't have to distinguish between them. I don't have to write P1 and P2 because they're the same number. Well, if P1 is 0.91, P2 is 0.91. If P1 is 0.00587, P2 is 0.00587. So under the assumption that they're the same, it doesn't make sense to distinguish them anymore. And for that reason, under that assumption, when I'm writing my standard error for the hypothesis test, I get rid of these subscripts, and I just have this P because, again, I'm assuming they're the same. Now, if I do that in this particular case, I end up with p times 1 minus p divided by n sub 1 plus p times 1 minus p divided by n sub 2, and I can factor out this p times 1 minus p. If you don't understand what I'm saying here, what I'd like you to do is go flip back in your slides to the standard error that we had when we did the confidence interval. Write that out, and then in place of P1 and P2, whenever you see a P1, just write regular P. And whenever you see a P2, just write regular P. And you'll see what I mean when I'm saying we can just pull these out, because there's a P times 1 minus P on top of both of these fractions, and we can factor that out. So that's where this formula is coming from. I kind of don't like this. It's a little bit like it looks easier, and in some ways it is, but I think it's a little more complex because it looks like it's different from what we did previously. And actually, this isn't different at all. This is mathematically exactly the same as what we had just a few slides ago for the confidence interval. We just replaced P1 with P and replaced P2 with that same P and then factored it out. All right, I'll stop talking about it. So how do we come up with P, assuming all of these are the same? Well, how we come up with our best guess of this P value, I shouldn't say P value because that's confusing. How we come up with this best guess of this proportion, again, P1 and P2 are the same proportion, we'll just call that P, is we have this P bar, or how I'd prefer to write it, this P hat. And how we come up with this single number guess is N1 times the guess for P1 plus N2 times the guess for P2. And remember, the guess for P1, we see how many people agree divided by a total number of people we sampled, and that's our guess for the proportion from the first population. And do the same thing just with the second population. That's our guess for the proportion for the second population. Plug in those numbers into this equation, and that gives us our guess for the overall value of P. This is a weighted average between these two. So if you remember weighted mean from maybe DA 291 or your previous stats class in general, this is your weighted mean of these two proportions. All right, so we've got these two proportions. Well, what is our test statistic? Well, our test statistic is in general going to be this same point estimate divided by the standard error that we had before. And actually, when we talked about this before, we said, well, point estimate minus the difference. But here, when the difference is 0, it literally is just the point estimate over the standard error. So we have the point estimate from the previous slide divided by the standard error from the previous slide. This is our test statistic. That's all we got. All right, so let's do a test based on this test statistic. So putting this together, can we conclude using a 0.05 level of significance that the proportion of households is aware of this? So looking here, we have our hypothesized value, and again, we're looking for an increase. So I'm looking for, if depending on the order, and this is important, depending on the order, if I put the after the campaign before the before campaign, an increase is positive. That is alligator facing to the left. If you did it the other way, if you put the before as the first proportion and the after as the second proportion, the alligator would face to the right. That would designate an increase. So the direction of how you put these is important. And again, it's important in the sense that you have to get it right, but you can put it right both ways. Like the fact that you put one as P1 and one as P2, that's not what makes it right. The fact that the alligator or the greater than or less than sign here matches with what you put where, that is what makes it right. So I don't care which one you say P1 and P2 is. All I care about is that this direction matches with whatever you said, and that it matches with the direction the question is asked. Then we specify the level of significance here. So this would be a good time to go on and pause your screen, give this one a shot. So go on and pause, try the critical value approach here, and we'll come back. All right, coming back to this. When I compute the test statistic, I plug in my numbers. My best guess for this overall P is 0.45. Why do I need this overall P? Because I have to calculate the standard error. This should say sigma not S. So I have to calculate the standard error here. In calculating this standard error, I get 0.0514. So I put the point estimate on top of the standard error 0.0514, and I get 1.56. This is my test statistic. Looking at the critical value approach first, comparing my test statistic to my cutoff. So if you look in your z-table for a one-tailed test, your cutoff at 0.95, that leaves 5% of the error on the top tail, is positive 1.645. Because it's a greater than or an upper tail test, we're seeing if R value is bigger than that 1.645. In this case, R value is not bigger than 1.645. So if we're graphing this out, we've got our shaded area, and R value kind of fell here. It was smaller than our rejection region. The shaded area is our rejection region. This is our fail to reject region. So in this case, we failed to reject, and we do not have enough evidence to conclude that the proportion of individuals who are aware of the client stuff is higher after the campaign. Incidentally, this is the same thing that we found in our confidence interval. We said 0, no movement, was a reasonable value. And here they're asking, can we conclude that it was greater than 0? And we're saying, no, we can't. 0 is a reasonable value. Using the p-value, recall that we use a computer or table to conclude the p-value. In this case, I get a p-value of 0.594. I do not have to multiply it by 2. This is a single-tailed test. I multiply it by 2 for a double-tailed test. So the p-value stays as it is. So I've got my p-value 0.0594. The p-value is bigger than alpha equals 0.05, that nominal type 1 error rate. And because p-value is bigger than alpha, we fail to reject. So p less than alpha, we reject. P bigger than alpha, we fail to reject. So we fail to reject the null and cannot make the conclusion that the awareness, or we don't have enough evidence to make the conclusion that the awareness grew after the campaign. And again, this echoes what we found in our critical value approach. It echoes what we found using the confidence interval. And it should be that all three of these align. If all three of these do not align, there was a mathematical calculation error. That is, you messed up one of them. All three of these are mathematically equivalent, so all three of these will align every time. I guess one place that it could not align is if you forget to align your alphas. That's probably the most common mistake that could happen outside of just fat fingering a number or something like that. So if you had a 90% confidence interval, but then for your tests you used alpha equals 0.05, then that could be a case where you don't get an alignment, something like that. All right, this has been a discussion regarding population proportions with two different populations and comparing those. And this ends our discussion of the means and proportions and the matched samples when we're comparing different populations. So this ends our discussion of what we've aligned with thus far with our previous hypothesis testing and our confidence intervals. In the next discussion, we're going to pick up with something that's a little bit different. It's still comparing two populations, but now we're going to be talking about how do we compare the variances of two populations. So we'll pick that up in the next lecture.